Now, a couple of things about this. In general, aldehydes react. I can sometimes form the species, and other times I cannot form the species. So it gets kind of confusing. What do I mean by this? Well, it turns out that this product is conjugated. Okay? If this R group here was a system such as benzene, right? If this had a phenyl ring here, I cannot isolate this because this elimination is so fast because all of a sudden I made a molecule that has a lot of resonance stabilization. Not only can I delocalize this double bond onto the carbonyl, but I could also delocalize it onto the benzene. And so again, I just want you to point that out, that under basic conditions, sometimes we will stop at this. In order to get the elimination, I often have to heat it to get this. Other cases, I can't isolate this. Okay, and again, I'll show you some examples in the PowerPoint in a moment that will illustrate these differences. Okay, this issue only occurs when I'm running this reaction under basic media. Okay, so if I'm running on base, I have to make the decision: do I stop here, or do I go all the way to condensation product? Okay, and again, I'll try to exemplify that. One other thing about this is I just want you guys to remind yourselves that the beauty of this reaction is I'm taking two molecules and I'm making a dimer of it. And this dimer basically has two function groups. It has a carbonyl and it has an OH. So right off the bat, I could do a lot of chemistry with this. If I treat this with sodium borohydride, I can reduce the aldehyde to the primary alcohol. This would be a 1,3-diol system. So if I ever wanted to synthesize a 1,3-diol, this would be an effective route. Okay. If I somehow dehydrate this by limiting water here, I form an alpha-beta unsaturated system. If I treat this system with lithium aluminum hydride, I also make an allylic alcohol. Okay. So I have a double bond here, and then if I reduce this with an aldehyde, I make a primary alcohol. On the other hand, if I use catalytic hydrogenation, I can reduce both the double bond and the aldehyde. Okay. On the other hand, if I just use hydrogen under these conditions, I basically reduce the double bond here, but leave the aldehyde. So a lot of versatility on this. Okay, so again, I just want you guys to get a scope of how chemists think synthetically. Now, what I'm going to do is I'm going to showcase the aldo reaction, but now under acid. Okay, so right now, up to this point, I've showed how we do this under basic conditions. So recall, if I'm under basic conditions, the intermediate that I need to form first is the enolate. Oops. Okay, and once I get the enolate reacts directly with the aldehyde. Okay, so that's what happens under base. I first form the enolate, and the enolate attacks the aldehyde. Under acidic conditions, you can't form the enolate. Instead, what you do is you basically change the keto-enol tautomerism. Remind yourselves that in acid, the enol tautomer is often favored. So I could affect this equilibrium here by basically employing acid. So again, Dr. Schwann should have taught you how to do this tautomerism. I kind of show it here. Okay, so in acid, the first thing I do is I protonate the carbonyl to make it more electrophilic, right? So the first step of doing acid-catalyzed aldo condensation is nothing different from what you already learned. Is first, I'm going to basically take this acid, protonate it to make a powerful electrophile. And now that I have a powerful electrophile, I can take this enol, push this electron pair here, and push this onto this double bond by nucleophilic addition and get the beta hydroxy aldehyde shown here as the protonated species. Okay, so it's a very similar reaction, except I'm not making the enolate. In acid, the new part here is I'm using the enol. But remember, enols are not as nucleophilic as enolates, so the first thing I have to do is make the carbonyl more electrophilic by protonating. Once I protonate the aldehyde, it can then react with the enol to give me this species, which is the protonated version. And the last step I have to do is basically remove this proton off the carbonyl, I'm sorry, to give me the beta hydroxyaldehyde. Okay. Now, it turns out in acid, we often don't stop here. In acid, we often go to the alpha, beta, and saturated system. In acid, the mechanism is not in E1CB because, again, E1CB says I must form an enolate. If I'm an acid, I can't form enolates because enolates are conjugate bases. So under acid, what happens is just what you've learned back in the first semester is the first step I'm going to do with the alcohol is make it into a good leaving group by protonating it with the acid that's present. Once I make the OH into a better leaving group as water, this guy can leave, but it leaves through an E2 mechanism where the water comes in, abstracts the alpha proton. So notice I have one arrow, a second arrow pushing here, followed by a third arrow to give me the alpha beta saturated system. So this is an E2 mechanism. Okay? So there's some distinguishers between doing the aldo under acid or base. If I'm in base, first thing I have to think about is I must generate the enolate. Okay? And I will form the beta hydroxy aldehyde system, but if I have something that's going to permit greater conjugation, it's going to dehydrate by an E1CB. In acid, on the other hand, I'm going to use the enol form, and basically the enol form will, once I get it to react with the aldehyde, the beta hydroxy form will react because I can protonate here, make a good leaving group here, and the elimination is by an E2 mechanism. Okay, so the elimination mechanism is different depending on acid or base. And base, it's E1CB, but in acid, it's E2. Questions?
Nope.
Okay. I know it's a lot to digest, but again, we'll